then I would like to introduce our first speaker, Charlotte Polett. I met Charlotte accidentally in one of the Horizon Europe online networking event. So I've not met her personally yet, but we met virtually in one of these EU matchmaking events. And it was more for brainstorming ideas and partnerships. And then we found that, actually, we're working on something similar, education. And she's working on the science or history of sciences. And Charlotte is now associate professor in Yangming Jiaotong University in Taiwan. She has a dual degree, dual PhD degree from Paris 7 and Paris 7 University and the National Taiwan Normal University. And she's working in Taiwan now, but at the moment she's back in, should I say back? She's in France for the summer, so she can join us today with the European time zone. Charlotte teaches courses on philosophy and history of sciences. She has also a dual career, should I say that? She's, as a philosophy teacher, she works on the development of and promotion of philosophy for children and new philosophical practices in Taiwan. But she has also launched recently an yearly event called the Philosophy Week and founded an NGO, Philosoph Kids. And as historians of sciences, she has a rather broad scope of research interests, including the transmission and elaboration of mathematical objects and procedures in Asia, historiography, and just to highlight a few. And she's also the author of a book called The Empty and the Full, the Year and the Way of Mathematics. So she's also a very distinguished academician. She's an Ordered Knight of Academic Palms and the recipient of the 2023 award of the Institute of France, which is a learned society or an umbrella organization of French academies. So I'm really grateful for Charlotte's acceptance of my invitation after this virtual meeting to talk about the influence and influence or coincidence about influence, about science from between India and China. So she's going to compare the pre-modern mathematical reasoning and objects from India and China. And she doesn't want to conclude who influences whom, but she would like to present it and let us think about it. Okay, so Charlotte, the floor is yours.
Yeah, thank you a lot for this lovely introduction and for the invitation after the talk we had during the European Union meeting. So we had to make a choice. Either I was speaking about philosophy for children in Taiwan, which is something going on now, but a bit too early to reflect on it, or history of science, especially math. And so we choose the maths, but it's a bit of a challenge because Queenie asked me to talk about India and China, the influence of India on Chinese math. And I can already tell you the conclusion of the speech. We know nothing. So I'm going, and the problem is that if I understood, I have 20 minutes to cover like two huge area with multiple epistemic cultures and also a time like if we have to take into account the Veda, it's like 3 millennium of history in 20 minutes, which is mission impossible. So what I'm going to do today, because as far as I understand, the purpose is to share our research and to see if we can work on something else later. So I'm going to present kind of landscape of what we have about China and India in mathematics before the 14th century. And we will see briefly some conclusion, what is conclusive, what is not. But I'm afraid I have to skip like all the mathematical demonstrations.
I don't hear very well, Charlotte. Can you maybe get
very
closer to your microphone?
Okay.
Yes, now it's better.
Better?
Yes.
Okay,
Yes.
so I will have to to skip like all the maths to go directly. So we have this, and this is what we get. And that's all. So we can come back on the math or on the methodology anytime you want during the question time. Okay, and let's see what we have. And I'm not used to Zoom because I'll share screen, share. As civil servant in Taiwan, we are not supposed to use Zoom, but as I'm in France, I guess it's okay. And slideshow. Yeah, it works, but I cannot see my whole screen. One part is missing. So influence of or coincidence, we will see that it's very difficult on the basis of the material we have to speak about influence. And the other thing is that, as you know, math is universal. So we cannot say that, like, if we have Pythagorean theorem in Mesopotamia, doesn't mean that it influenced Greek, who influenced, like, we don't know. So that's why in math, it's difficult to say who influenced and how. And well, we'll see some difficulties later. So I will focus only on pre-modern math, that is, in China, there is a big change after the Ming Dynasty. I don't have time to detail what, but why. But we are going to focus on the sample I'm going to show you. Let's say it's 3rd century to 14th century. So we will see some object text and the difficulties we have when we study that type of text. Alors, mainly, one of the difficulty is in literature when you want to read some research. You will find lots of research about East and West, but West is Europe, not India. There is very few things about India and China, and there is something like a strange enterprise. Why should we compare these two areas? We will see that we will not focus on the common point. If we focus on the common point, that would be like most interesting results. So our purpose is to show the different strategic objective, like mode of systematization, style of reasoning, and it's only on focusing on difference that you will see those specificity. And only once you have the difference, then you have a byproduct, and the byproduct is to raise question on possible transmission between areas. But areas here are big, and we have to first identify who is doing the math, what context, who is reading, what type of text. So very important thing is go back to the text, the content of the text. So we have to be careful when we speak about influence, transmission, because we will reach concept of boundaries, like what we name China or India. We see often the name of Chinese traditional math or Indian math. If you think about it, nobody talks about German or French math. So why Chinese and why traditional? So there is an important question of historiography behind it. We cannot discuss that today, but that's part of the topic. Okay, so the method we use here is go back to the text and use philology. That is textual analysis on how objects appear in the text, how they were used. And we have to think about mathematical text just as the tip of the iceberg. Mathematics, science is something we do, not something we read. So the text is just a small part, and we have to reconstruct the whole environment behind it, which is more like archaeology or paleontology, if you want. And we use tools from philology, and only once we have the whole analysis of the text, then we can confront it to mathematical transcription and modern tool, computer program, editorial material, and try to avoid to apply modern concepts on ancient math and cognition. We will see that we reach material from cognitive psychology when we work on that type of text. Alors, directly, I'm going to show you what we have, what works, and what is not working. Alors, of course, when we think about India and China regarding scientific, once again, we have a problem here with what we name science. Is the first one we have is in mind is Buddhist contact and the road of Buddhism into China. Here in math, we have 4 names, Yixin, Faxian, Xuanzhong, and Siddhanta Gautama. But unfortunately, we have almost no information. But what we have, which is more interesting than just 4 names, is calendar. And we can study calendar making and compare the technique and see some specificity. So that's not my field, but I strongly advise you to see Michio Yano from Osaka University's work, which is amazing on that point of view. So what we know about the Buddhist contact, we have only very fragmentary evidence of Chinese, Indian cultural contact before the rise of Buddhism around the 4th century AD. And we have a little bit more information on the spread of medieval Sanskrit mathematical astronomy into the northern Himalaya around the second transmission, that is the revitalization of Buddhism in Tibet in the 11th century, but largely influenced by esoteric Buddhism in India. And the chief vehicle seems to have been the work, the Kalachakra Tantra, which was translated in Tibetan and Mongol. Here we have only very few researchers like Ohashi who are able to work on that type of text. So here there is like all the work remains to do. Now, if we want to know a little bit more about Gautama Siddha from Chang'an, so he's an astronomer, astrologer, compiler of Indian descent, known from leading the compilation of treatises on astrology at the Tang Dynasty. We owe him a translation of Navagraha into a Chinese translation, but based on Vahamira. But the text is not available. That's why I say we don't know how it was influenced and how it worked, because we don't have any remaining text.
Your voice is fading again, Charlotte. Okay, sorry.
Trying to do my best. So 2 interpretations here, either introduce the Indian numeral with 0 in China to replacement of the counting road, which I highly doubt because counting roads were still in use. We will see them later. Or maybe more, he insisted that Indian numbers were written cursively with 1 stroke and 0 with a dot in an empty space, which is more likely. So most of the texts here are written by the Buddhist pilgrim in China have never been examined on the scope of research of history of science. Only religious and sociological content were discussed, not the scientific content. So once again, there is a field for research here. Now, the key of debates between India and China.
The sound is fading again. Sorry.
Yeah, no,
it's good.
Yeah. So we have several main topics. So the Buddhist text and numeration system, because both systems are positional system, they are base 10, and they use 0, positional 0, sometimes as operator, that's something else. But the main difference is, as we see here in India, we use just 1 stroke to name, to design all the digits and to directly operate with them, while in China, we have several systems for transcription of number, the one you know in Chinese, which you use all the time. And mainly the other one, which is made of road numeral, which were like probably small bamboo stick used on a counting surface to do the operation. Here we have polynomial, and this is an equation. So, well, I won't lose time to read that. If you want, we can come back on that. But this and this are both second-degree equations from 13th and 14th century.
So here you see the way of writing number, the one you already know in China and the one we use in Sanskrit, and it's difficult to compare the two sources when it comes to talk about influence of numeration. It could be just a coincidence. These are the bamboo sticks used for computing. We have no trace of them in China. We just have one sample from Korea. The other common point we have is the list of large numbers we find in sutra, like the one from Yajurveda, which is up to 10 power 12. We have other bigger one and bigger. Well, I won't detail all this list. They were translated into Chinese, either using meaning, like Nira Bilapriya was translated by Bukoshwo Zhuan, like for the really big number. So we have list of number like that, but they were never used in astronomy or any mathematical context, just list, and they were never studied really as such and how they were translated into Chinese. So once again, we have an open field for research, but we know they were never used in astronomy. Another topic which is more interesting than the Buddhist channel is the indeterminate equation in astronomy. So we have the procedure, the Dayan procedure in China, but we have also something that look really alike, the Kutaka pulverizer in India. The oldest occurrence of this procedure is found in Sunzhuanjing, 4th century. And then we have a collection, a series of similar procedure in Aryabhata, Bhaskara 1, Brahmagupta, Mahavira, and Bhaskara 2. And then we have the most general and achieved formula for this procedure in Qingjiusha in 13th century. Influence, coincidence, who influenced who? That's a long debate and a long story in historiography. I wrote a whole article on that if you're interested. But let's say that some people say that the Chinese copied the Indian. So the Indians, some people say that the methods are really different. They just look the same, or they are similar, not the same, different, Chinese, India, and so on. So there is a huge competition, and culture as, I would say, culturalism or nation are not really far behind a story in history of science when we speak about Chinese math, Indian math, or even Greek math in Europe. So we have this problem behind it here. So we cannot conclude about the resemblance between the two theories because it's also depends how they were used. And we are sure there were absolutely no contact between the Indian astronomer and the Chinese mathematician, and they don't work in the same field. In India, math is related to astronomy, where in China, especially with Qingjiusha, it's something else, really something else. And it's not astronomy, and it's not educational context. It's more Taoist context with some other research I hope I will have time to show you in a few minutes. Another topic, once again, you see there is a whole continent of history to explore. And once again, that's just the beginning, and we have only 2 or 3 people working on this field. So we find lots of collection of problems. Actually, Indian text and Chinese text are made of collection of problems, but the purpose is not problem solving or education. Like for instance, here, one of the most famous one is the broken bamboo problem. Here you find the 14th century representation, and here you have the broken arrow in Lilavati. You have lots of, sometimes you find problem with the same data, but the narrative is different, or sometimes common narrative, but different data or different context. So there is a room for a whole study about connection between problems. But the difficulty of the topic is that we have first to connect all the problems inside Sanskrit text and Chinese text before being able to relate these two. So as far as I know, the only person who worked on the Indian area on that part is Hayashi, who made beautiful connection between Bhaskara and Mahavira. So the practice of lists of problems is something really specific, and we will see, I hope, why this practice is interesting here. Another it's just anecdote, but it's quite interesting. There is a Chinese song, maybe a lullaby, or maybe something we recite to learn to study math. which was analyzed by one of my colleagues, Alexei Volkov. And the song talk about the wind for 5, the sun for 12, or something like that. And this is interesting because Sanskrit texts in mathematics are versified. So you cannot make poetry with number 1, 2, 3, 4, 5. So you replace them by synonyms used from all the mythology. And indeed, for 12, this is Surya, the sun. For 5, it's Vayu, the wind. For 2, it's Ashvin, the twins, and so on. You can use like many synonyms. And this is a coincidence that we find exactly those meanings, these Sanskrit synonyms, inside a Chinese popular song. Once again, we don't know how it works and how it arrived there, but you see, we know there is some connection, but we still have to study them. This is what's happening when we focus on resemblance. It's difficult to have conclusive results because of the lack of material. I think the most interesting point, and I will be very fast on that one, I will just show briefly how it works and how the conclusion, what the conclusion here is, and we can come back on this. I think the most interesting the most interesting, it's dealing with cognition. The most interesting result is about combinatoric and a magic square, arithmetical triangle, and combinatoric spirit, like how to calculate the possibilities, the various possibilities to combine things. We see lots of elements from different tradition. Here you have arithmetical triangle by Jiaxian, represented by Zhu. Here we have a 19th century, it's not really a manuscript from India, but you have many other sources. You have a lot of text like that into also in the Middle East written in Arabic. And here this one from Yuan Dynasty China, and you see those are Hindu Arabic numerals inside. That's interesting. So I will come back to this combinatoric spirits by showing you 2 texts which are not related at all. So on one side, we have, for instance, the work of Li Ye, Yiguyan Duan, or Zheyan Haijing, 2 masterpieces from late Song, early Yuan dynasty. And on the other side, a work by Narayana Picha Ganita Vatamsa, and here I will focus on Ganita Kaumudi from 14th century. And we know nothing about Narayana, but there's something we are sure about. They never met. There is no way they could read each other. So this is how the 2 texts look like. So nothing to do with magic square, because this is a geometric representation of an algebraic equation. So not a magic square at all, not combinatoric. It looks like just a simple procedure to explain some algebraic solution on how to compute an area and how to find the roots of simple quadratic equations. So from mathematical point of view, it looks like an easy, basic beginner text. On the other side, the Sanskrit counterpart, it's also algebraic. Here you find equation, and here list of problem as the other one. The first one in China, 64 problem. We don't know why we have this collection of problem. And here a collection of sutra, and each of them contain a list of problems. I show directly, I skip the math. I just show, like in China, if you want to think about those diagrams you've seen about algebra and geometry, there's something really important you need to catch. You must forget all your Euclidean geometry you have been learning in high school and all your education in that. Think about space differently. You have to think of area as the move. We don't speak about segment and dimension, but about area. We open them, we cut them, we pass them. It's all about movement. On the book, or what you do as a mathematician, you have to see something, draw something, and visualize something. And imagine you have to do this exercise on a multiple collection of problems. So this is a key to understand what's going on. Let's see that the proof of are never written, but it's important to visualize this. All this collection of diagram and diagram are a key to understand mathematical content. Now, the way to order those problems, it's not made for students from easy problem to difficult one. There's something else. we see a way of ordering figures, ordering a geometrical figure. So the first one is according to the shape of the area, a square with a point inside, or a round field, circular field with a square point inside, and so on. Iteration, alternation, like we repeat something with two type or other type of figure. Same thing then with the data we use to construct the polynomial, which is a short, long, it's always like that, short and long. That is, we alternate, we do an iteration and alternation of two type of length, short one, long one. Then you have the visualization. There is no like 30 type of visualization movement. You can do transformation on the figure. There's only 6 type of them. So it works like arithmetic bricks. So you remove the corner. This is what you do when you visualize. This is the one I showed before briefly, like open one square, past some area because you remove too much. You can recognize from the vocabulary of the text. I skip the philology. Expand the area, transform a circle into 4 square area by using pi equal 3. Or this one, like diffuse, this is how I translate it sequentially, like to melt 2 areas. And when you combine all these artifacts, figure, length, type of arithmetical type of visualization, you see that the web of the problem is organized according to something else, which is a combinatoric system. We have 64 problems, short, long distance. So in fact, the type of equation are not, it's not a book about algebra, it's a book about combinatoric with spirit of magic square. And it's not written in the text, it's hidden. And if you look at it from Indian point of view, you find something a little bit similar. We won't speak about area, but we speak about prosody. So we have alternation and iteration of syllab. And I try to be very fast, so I'm skipping many things. I'm really, really sorry. So we have a combination here of lagu and guru syllab, like heavy and light. You have some strict rules to work on poetry, and this is very helpful when you read mathematical text, because if you see a metric mistake, it means that the metric, no, when you see a mistake, it's not the metric which is not correct, it's probably the math. So it helps to correct the math. So the rules are stated in the Chanda Sutra by Pingala, and you have a variation with the 4 syllab. I skip all the rules, but let's say that we have Narayana working the same way on combinatoric here, trying to determine the configuration of form under given constraint and to generalize this Prataya rules, that is the metric rule, in combinatoric and use it in a process of generalization. Lié use also this combinatoric spirit for generalization and with a target of demonstration. And we see here with construction of only ordinary magic square, but also variant made by combining multiple magic squares. So behind the text, we see some common points. Influence, no. Coincidence, don't know, but clearly a specific type of reasoning which is different from what you see in Euclidean style of reasoning. A new style, another style, a common point between China and India when you look at the target, the objective behind the text, which is using combinatoric to express generality. Okay, so here as a concluding remark, so we see that what we call algebra is a shape of analogical problem. We have a dynamic reading from cognitive point of view. You have to visualize movement and alternation to understand the logic of pattern, to focus on search of operation and action to be performed on pattern, and this is determinant. What we call geometry is in fact a way to grasp mathematical argument on construction for algebraic purpose, that is equation and polynomial. This is something you won't see in Europe before 16th century. Then what we call mathematics is in fact a research of combinatoric, on work on change, transformation with a purpose of generality and demonstration. And here we see that we compare Indian and Chinese algorithmic construction for polynomial. We see strongly a deductive skill. I say that for all the work in history of science, where you will find that there is no proof or demonstration in China or India. You will find many of them. If you find one of them, just put it back on the shelf. So there are unwritten practice on verification and demonstration. These are not written because this is something you do. The text is just a small part of the activity. So we see here that list of operation and especially list of problem conveys mathematical meaning. They are not just for problem solving or educational context. This is something else. So I tried to be like really brief to show like all the things we can do in history of science here in that field. I hope it was not too like horrible to follow and not too technical.